Our final presentation has the title Breakthroughs in Aerogel Technology, Opportunities and Challenges. And our presenter, Aaron Baskerville from Aeroshield Materials, is co-founder and vice president operations. Aeroshield is an MIT spin-out developing super insulating transparent aerogels for windows with the goal of bringing the state-of-the-art energy efficiency into buildings at an affordable price. Aaron holds a master's degree in chemical engineering and an MBA from the MIT Leaders for Global Operations program. Before founding Aeroshield, he worked in both management and engineering consulting. Please welcome with me Aaron Baskerville.
Hello, everyone. Thank you for having me here. One of the big questions that we asked ourselves as we were thinking about Aeroshield and the potential of aerogels is, what if we could take the world's most insulating material ever created, designed to protect equipment in the coldness of space, and apply it to the least insulating part of the building envelope, which is the windows. It's my pleasure to be here today to talk to you about breakthroughs in aerogel technologies, both the opportunities and the challenges, and talk a little bit about where we are in the commercialization pathway for this technology. A little bit of background about our team and Aeroshield. My name is Aaron. I'm the co-founder and one of the VP operations of Aeroshield. The fundamental research for Aeroshield was done by our CEO, Dr. Elise Strobach, during her PhD at MIT, and our co-founder, Dr. Kyle Wilkie, who was a PhD in the same lab at MIT. But really, the focus today is much broader. What is happening in the world of aerogels and their application into things like insulated glass units? So today, my goal is to talk a little bit about why people are excited about aerogels in the first place. What value do they have to the built environment and the glass industry? What are the challenges that have historically followed aerogels, and why haven't they seen the adoption? What recent advances are going on in labs in North America and Europe and Asia? And then the opportunities and challenges going forward. So I like to refer back to this study done by the US Department of Energy called Pathway to Zero Energy Windows. This came out in 2022, and in it, the US Department of Energy sets a target for what they think the next generation of windows needs to do in order to serve the needs of the built environment. And in it, they set advanced U-value targets while maintaining a price point that provided valuable payback periods for home and building owners. Now, in this report, they highlight that triple panes are kind of the incumbent technology if you want better than double pane performance. But they also highlight 3 state-of-the-art technologies that they saw as having high potential to provide better than triple pane performance at a lower than triple pane price. And so in this report, they talk about aerogels as an aerogel double pane unit that can outperform a triple, about thin triple technologies, as well as vacuum insulated glass. And so I think it's fantastic that, just in this session today, we've actually seen presentations on all the state-of-the-art technologies that they highlighted in this report. Obviously, my presentation today will focus on the aerogel side of the world, and I'm really excited to share the stage with people who are working in all of these areas. So let's maybe start with, what is an aerogel? Aerogels are a class of material that are typically 97% air. So they're formed of a nanostructure that traps air inside of their pore network, and it creates the very interesting set of properties. Aerogels were originally developed by NASA to insulate spacecraft because they are some of the most thermally insulating materials ever created. They are super light, and they're fire resistant. But they've always been blue. The science of why aerogels are so insulating is because that they really target 2 of the main modes of heat transfer that we see through any material, but windows in particular, conduction and convection. And so the aerogel material, because it has this nanostructure, because it's 97% air, there's very little solid material for something to conduct through. But because it has this complex pore network, it's essentially trapping air or argon or krypton or whatever you've put inside that IGU inside that pore network, and it prevents any sort of conduction inside that IGU as well. So you have this dual benefit of having very low conduction, very low convection. But the aerogel is transparent to most radiative forms of heat transfer. And so what that enables is that you are not changing your coefficient, your solar heat gain coefficient or your visible transmission. You can apply whatever low E coating is most suitable to your geography, to your climate zone, but you are dramatically reducing your U value. So you're getting U value benefits without changing your solar heat gain coefficient or your visible transmission, and because of the lightweight nature of the aerogel, you're not changing your weight or your thickness of your IGU either. So really think of this as a coating that is focused on improving the U value without affecting anything else. One of the other important aspects of the aerogel when it comes to sustainability is the lower embodied carbon that an aerogel material has. Because it is 97% void space, there's very little physical material that goes into making this coating. And so when you compare it to an alternative technology to get high performance, something like a triple pane, adding another pane of glass, as we all know, is a material that has very high embodied carbon. So if we can replace that additional pane of glass with an aerogel coating that has very low embodied carbon, you're ultimately going to have a product that has a much lower carbon footprint than the triple pane alternative. And then finally, I think we heard this in the presentation about thin glass as well. There's a weight benefit to the aerogel. The aerogel is actually going to be much less heavy or less dense than another pane of glass, even a thin pane of glass. So there's an additional sustainability benefit because of the reduced weight of the resultant unit. So that's going to affect anywhere in your supply chain. So I've talked a little bit about aerogels and the material properties of them. But what does this look like in an application? And I just want to get people's heads wrapped around the concepts or the prototypes and that AeroShield is building right now. You actually have an aerogel bonded to glass, almost like a glass coating, typically opposite the low E. So you'd be either surface 3 or surface 4, depending on where the low E is. And then you could still have this space, right? So you'd still have argon or krypton or whatever gas fill that you want in the middle. And really the benefit of doing it this way is that you can create a window or a unit that has better than triple pane performance inside the exact same double pane glazing pocket. And you're using the exact same type of glass. You can use the exact same spacers. You can use the exact same sealants that you would use in your standard window manufacturing process. And you're going to get a higher performance unit. So hopefully this is something that seems very exciting. You know, you have a coating for glass that can improve the performance of the window to the point where it's better than a triple pane. So why haven't we seen rapid adoption of this technology in the window industry? So I want to start by walking through a little bit about the history of aerogels, what they have looked like in the past, and then where we're going today. Historically, the main challenge with aerogels is that as they were developed by NASA, they were never really starting with this starting point of transparency. That was not the goal. It was super insulation. And so subsequent research into aerogels has always struggled with this starting point of a fairly high haze value, very low visible transmission. You can see over time that you're looking at TVIS less than 80% for historic efforts at making aerogels for windows. And so this has resulted in products. There's skylight and daylighting options that use aerogels to kind of create a translucent effect with super high performance, but it's really never been used in vision glass because of some of these issues. One of the other issues that comes with aerogel processing is it's hard to make big sheets of aerogel. So aerogels have a very specific manufacturing process, and historic issues have been how can you make sheets large enough for a vision glass, which has resulted in people cutting them into different shapes and sizes and putting them inside of an IG, which creates really interesting patterns and great prototypes, and you can test the thermal conductivity, but this is really not the mass market product that you would hope to see out in the world. And finally, the last challenge that aerogels have historically had is in passing all the durability testing that you would need to see in the world of Windows, ASTM 2189, 2190, the thermal cycling challenges that that the window industry faces. And so some historic examples, there was an ARPA-E program in the late 2010s focused on how could you make aerogels on glass. And one of the challenges was as the aerogels were processed, they would shrink and they would crack on the glass. And that really resulted in, again, windows that would not be used. On the right-hand side, you see some early AeroShield units where we had a seal failure in our IG, and the aerogel being exposed to high moisture content essentially breaks down, and you get optical defects that are, and mechanical failures that are insurmountable. But there is hope, and there has been a lot of recent advances in aerogel science and manufacturing that have brought them incredibly close to commercialization. And so I want to walk everyone through some of the reasons why we are seeing major advances in aerogels for windows right now. And the starting point was clarity, achieving the world's most transparent aerogels. And I know we have a lot of optics nerds here, so I'm going to go through a little bit of the science. Aerogels are a pore network. And this light can interact with this pore and essentially deflect. And that was kind of the fundamental challenge with haze, is that the light would interact with this pore network, deflect, and you would get this kind of hazy nature because the light was refracting through the aerogel pore structure. And what Dr. Elise Strobach, our CEO, found during her PhD research is that you can actually model the interaction of light with these aerogels through Rayleigh light scattering. The same reason that the sky is blue is the reason that aerogels were blue, is the light diffracts, and the fundamental equations basically stated that the particle size and the pore size inside that aerogel network are what govern the way that light interacts with it. When we think about something like a typical aerogel that you may have seen, those really blue, hazy ones, the pore size of those aerogels is typically about 80 nanometers. The optimum is somewhere between 6 and 10 nanometers. And so the fundamental research that we found was like, this is the optimum. Now, can we make repeatably an aerogel that has a very tight pore size distribution around the optimum for optical clarity? And really, this was the starting point from the research at MIT that led to the transparency that we're seeing today in various different research labs across the world. What you see on the left would be aerogels that had this more traditional 80 to 90 nanometer pore size, and on the right, aerogels down to the 6 to 9 nanometer pore size. And so when we think about what is out in the world today, what aerogels, what work is being done in aerogels, there's a group out of UC Boulder that are working with aerogels derived from natural sources. These are aerogels on about a 1 meter square size, and they have visible light transmission of about 99% at 1 millimeter thickness, and about 97.5 at 2.5 meters thickness. Haze values of about 2.8% at 2.5 millimeters thickness. And it's a really exciting result. This was published in Nature, and if you are interested, I highly encourage people to look into the work that they are doing. But I think one of the important things as you think about, as a window industry and someone who is working in this space, aerogels are insulators focused on conduction convection. And so the thickness of the aerogel is going to modify or change how much insulation you are actually getting. So achieving 99% visible transmission at 1 millimeter is not as valuable as achieving 98% at some higher value of thickness. And this is really where AeroShield is focusing on what is that U value performance that creates a step change in performance that gets the window industry excited. And so AeroShield, what we do, we are focusing on aerogels at the 4 millimeter thickness and greater. So achieve 98.4% visible light transmission at 4 millimeters of thickness, and haze of about 1.5% at 4 millimeters. I encourage you to come visit the booth in the step change space as soon as those prototypes arrive from wherever they got lost on transit. But hopefully by the end of today, we will have them from the airport. But these are some of the very early prototypes that AeroShield had made. I also think that it's really important, as we think about aerogels, it's not just the bulk properties. How do you make an aerogel that is transparent? How do you create the processing methods that meet the exact same standards of the window industry? And so this is an area that we have been focused on for the last couple of years. We now have a transparent aerogel. How do you get one without any sort of defects that would not pass something like an ASTM C1306 or for low E coated glass type of standard. And so back in November 2022, when we made aerogels, these are projections from our projection system. You were seeing all sorts of defects because of the way that the aerogels were produced, to the point where today, we're in 2024, we do not have any of those defects inherent in the aerogel. One of the other big things that you have to see is size and scale. You have to be able to make large sheets of this at high quality. And one of the historic challenges of aerogels, as I mentioned, is that in processing, they would tend to crack as they shrank. One of AeroShield's breakthroughs is making aerogels that no longer shrink in processing. So we have a processing step that eliminates the shrinkage. And so this photo on the left here is an aerogel-insulated IGU at the entry and patio door size. And so this is something that I don't think anyone else has achieved, and this is a very recent advancement, literally this spring, to be able to make IGUs at this kind of form factor that are aerogel insulated and provide this high level of performance. There's also work being done in Asia focused on how do you make aerogels that are much larger using other sorts of drying methods that don't require the same capital intensity of historic drying methods. So some very exciting work going on in the aerogel space. And finally, when we think about aerogels, they have to pass all the standard industry tests. We think about these in two ways. What are tests that are intrinsic to the aerogel? And then what are tests in terms of how you're integrating the aerogel into an IGU? So intrinsic to the aerogel, UV stability, off-gassing, compatibility. Tests of aerogel and IGU integration would be all your thermal cycling, temperature cycling, SLAM testing, mechanical testing. The aerogel itself, especially silica-based aerogels, are very stable. You're talking stability. Previous papers that we've published, the aerogel was stable to about 600 Celsius before it started to degrade. And then we've also passed thousands and thousands of hours of UEA, UVB, and we feel very confident in the thermal stability. But some of the recent breakthroughs, and we'll see if this video plays, are in the integration. So this is really how can you bond an aerogel to glass to create an IGU that can pass mechanical testing as well. So this is aerogel insulated units mounted in a door. These have been slammed 50,000 times. One of those units has the aerogel on kind of the back pane. One of them has the aerogel mounted on the front pane. And this is a huge advancement as well. If anyone here has ever handled an aerogel, it is a fairly fragile material. It's a coating, right? So to be able to put this into an IGU and to be able to slam it 50,000 times and not see any delamination, not see any cracking, is incredibly big advancement. So as we think about the opportunities and the future areas that we're working on, we are currently working with Lawrence Berkeley National Labs to integrate the aerogel material into the window simulation software. So we've done a number of tests. We have kind of this package is available now with the thermal conductivity and all the properties that would enable us to simulate all sorts of different window performances and window configurations. And ultimately what this has resulted in, so this is some of our work, and unfortunately, if people want to talk about specific values, happy to do that with anybody. This is some work that we did with some customers on a residential IGU with 3mm glass. Basically, you see a huge step change in performance when you compare a double pane to a double pane with aerogel, to the point where you can get aerogel double panes, right, on the right-hand side of this graph, aerogel double panes that are outperforming triple panes. And so this, I think, is an incredibly exciting result. And for people who are looking to either have a limited number or limited thickness, reduce weight, reduce the number of low-E coatings that you're putting into your windows, the aerogel can provide this huge performance boost to any sort of glass stack. But we also invite anybody to come up with their ideas. I mean, we want to be a tool in the toolkit of your developers and designers to say, what would you do if you had a super insulating transparent material that could be put inside of an IGU? Finally, I think some of the things that are interesting and that we ask the glass industry about everywhere we go, how do we certify this? This material is very interesting because it has this open pore network. When we do material testing, typically when you do the measurements on a heat flow meter or something like that, you're just doing it in an open space on the material itself. The aerogel, when you put it inside an IGU, that argon is actually going to infiltrate the pore network. You get better performance of the aerogel itself when there's argon in there because the argon is in that pore network. But it's very hard to measure it on a heat flow meter. So right now the only measurements we have are really in the IGU, and you back calculate or solve for the thermal performance of the aerogel. So I think it's a really interesting question on how can you measure just the aerogel so that we can get better values for that. Because right now we're not giving ourselves even full credit when we do those thermal simulations with NREL. I think the other thing is shipping. I mean, shipping aerogels are challenging. Today, we take aerogels off the line, put them into an IGU, and we can ship that IGU. But shipping aerogel itself, or even aerogel-coated glass, is a challenge. So something that we're thinking about and are talking to the glass industry about what is the best way to do that. And then finally, the optical quality and developing ways to, I know there's plenty of inspection people here, how to inspect aerogels in line to enable the high quality that the window industry is looking for. So with that, I just want to thank everyone. We are really excited to collaborate with the window industry. We know that you guys have years and years of experience of how to turn these types of innovations into products, and we're really excited to work together with you. So thank you very much for hosting, and I look forward to talking to people more.
Thank you very much, Aaron.